All right, we're going to do another related rates example here. This one's about marshmallows. So let's say we're in a dorm and we can't have an open flame, so we've got to make our s'mores by putting a marshmallow in the microwave. Now, if you've ever put a marshmallow in a microwave, you'll know that it starts expanding. If you haven't done it and you won't want to, and you decide to try it, just make sure you watch it because it gets really big really fast. Okay, it's kind of funny. So we're going to put our marshmallow in a microwave and we're going to assume that as it grows, the height is always 3 times the radius. So that's going to give us maybe some information. Maybe we'll write that down just as like they gave us some information. So let's say the height is always 3 times the radius. In these types of problems, they might give you kind of clues like that. Whenever you see a clue that's, maybe a kind of a strange fact that's not always true, but in this problem it is, it's good to just like write down what that means because you might need it later, and you probably will because there's maybe a reason that they told you that this is the relationship. Okay, so when I turn on the microwave, the marshmallow starts expanding, and it's expanding at a constant rate of 2 centimeters cubed per second. Let's look at the units of that. Centimeters cubed tells us that this is a volume, and the marshmallow is expanding. So this is telling me that the volume is getting bigger at a rate of 2 centimeters cubed per second. Okay, we want to find the rate at which the radius is increasing when the radius is 4 centimeters. So we want to know this rate is what we're trying to find. And this is our when the radius is 4 centimeters. All right, let's come up with a way to maybe, well, first let's sketch our picture, right? I'm doing my little acronym here. So sketch, I'm saying the marshmallow is typically a cylinder. So let's say, oh, I don't know why that did such a, there we go. That's a pretty good cylinder there. And let's say I've got this and this side, and then like kind of connects like that. Pretty good. There's my marshmallow. And let's say the radius is that portion, and then the height is this portion. Now, for a lot of equations for cylinders, you need to know the radius and the height. So like the volume equation, the surface area equation, all those kinds of things. The radius and height are important. All right, so there's our sketch. Now let's write down our rates. I sort of already started doing this. Just whenever I read these types of problems, I like to take notes on them so that I know kind of what's going on and break it down into smaller pieces. So as you read these problems, like you'll read a sentence, ask yourself, like, what does that mean? Is there some math in there I could write down? Okay, so let's write down our rates. We're told that the marshmallow expands at a constant rate of 2 centimeter cubed per second. I sort of already wrote down what that means because I was taking notes on this problem. This centimeter cubed tells me it's a volume. So I know dV dt equals 2 centimeters cubed per second. And we're asked to find the rate at which the radius is increasing. So that tells us that dr dt is what we want to find. That's what we're being asked about. Okay, so those are our rates. Now we need a way to relate related rates, relate the variables of these rates, v and r. We're going to do that in an equation. Okay, so we're on this step, equations. Okay, now the equation for the volume of a cylinder is pi r squared h. Okay, so we have our equation for volume. And so we've got let's take a little inventory here. We know something about volume. We know something about radius. There's this kind of pesky height in here. And ordinarily we'd be like, well, I don't have information about the height, so I don't know what I'm going to do there. But we were told that the height is always 3 times the radius. So I wrote this down that if the height is always 3 times the radius, h equals 3r. So if I want this equation to only involve little r, I need to make this substitution that wherever I see h, I'm going to put 3r. So this is pi r squared, and instead of h, I was told just in this problem, right? Not in general, not like forever and ever, but we have some special marshmallows here where this is always happening. So for this particular problem, the volume looks like this. Okay, so I should say for this specific problem, this is not like a rule that would be applied anywhere, just right now. Okay, so now I have volume in terms of radius, and I can go ahead and think about taking my derivatives. Okay, so maybe I'll write this a little cleaner. V equals 3 pi r cubed in this case. So here height, we're told, was 3r. Okay, so we're going to take derivatives with respect to time. The derivative of v is just 1, but because I'm taking derivatives with respect to time, I need to write down dv dt. Then I need to take the derivative of 3 pi r cubed. 3 and pi are both constants, so they just sort of hang out while I take the derivative of r cubed. So I have 3 pi. Oops, could write that a little cleaner. And then the derivative of r cubed is 3r squared. But because, again, r depends on time, I have to put dr dt. So really, I've got 9 pi r squared dr dt. Great. So we just did derivatives. Now we need the when. When we're trying to solve for something when something happens. And the when here is when the radius is 4 centimeters. We don't have to do any unit conversions because my volume's in centimeter cubed. My radius is in centimeters, so everything has the same units, or at least the same like length units. So our when here, we know that the volume's changing at a rate of 2 meters, or centimeters, meters, that's an enormous marshmallow, 2 centimeters cubed per second. Remember, here's my dv dt, so I'm going to replace dv dt with 2. We're asked when the radius is 4 centimeters, so I'm going to replace this r with 4. So I have 2 equals 9 pi, r is 4 squared, dr dt. dr dt is the thing we're trying to find. So maybe I'll put this on the next screen and I'll remind you where all these things came from. This part was dv dt. This was 9 pi r squared. And this is what we're trying to find. Okay, so really I've got 2 equals. I just want to make sure I have all of the things right now. Okay, 2 equals 9 pi times 16 dr dt. And I want to solve for dr dt. So the question was asking me about the rate of the radius. Again, all these are just numbers, so I'm going to divide this product on both sides. Right? So it goes away here, and I'm left with this. So dr dt equals 2 over 9 times pi times 16. And let's simplify this a bit. 2 goes into 16 8 times. So I've got, 1 over 9 times 8 is 72 pi. And then lastly, we need units. The units of length in this problem were centimeters. So the units of the radius are centimeters, and the time was in seconds. So this is centimeters per second. Okay, just to write this a little cleaner, my final answer, 1 over 72 pi centimeters per second. All right. That is the end of this problem. Let me know if you have any questions.